And here we have my Arduino code. Up here I floated fs because we're going to need to divide it unevenly later, and then I declared the baud as specified. And down here I floated the pot to analog read 1 so that we could determine the sampling frequency according to the potentiometer input. Then, to divide fs into 4 values really, I needed 4 regions from 0 to 1023 for each value. I used if statements to assign those frequencies to ranges of the potentiometer input, which are these right here. Then down here, I floated dt 1000 n times 1000 to make it milliseconds. Then I had some serial print stuff to set it to 500 hertz initially for the first exercise. Floated x, which is analog read 0, which is the N-scope reading, and then printed that so that I could print it over in processing. And then delay microseconds, which is dt times 1000 to convert it to microseconds. Here we've got the 75 hertz sample. We have 100, 142, 200, 500, and it shows aliasing at 100, 142, 200, and a clean sine wave, no aliasing, at 500. Just going through here, I guess. Sorry, I'm doing these recordings in post. Here's the 100 hertz, so we get a clean sine wave here at a sample of 100 hertz. Then we get nice aliasing over at 142, 200, and some aliasing at 500 as well. At 215, we get aliasing at fs equals 100, and we get aliasing at 142. We get a clean sine wave at 200 because it's pretty close, and then we get aliasing again at 500. At 300 hertz, we get aliasing at 100. We get a sine wave at 142 because it's probably close to 150, and then aliasing at 200 and 500. Here we have my aliasing calculations using z-fold diagrams. Going through, there's a lot of scratch work because I was going quite fast and ended up making a lot of errors. But I think we came out just fine as I went through and made sure that my z-fold diagram logic was okay. And this is the equations for all of the frequencies that we needed to look at. Here is the summary table showing my actual VSA sampling rates, along with the Nyquist frequencies and the Nyquist rates for each one. The aliasing, as you can see, pretty much cleanly corresponded to most of the alias frequencies that you would see in those harmonics that showed up in the screenshots from before.
So here's my circuit. We have the potentiometer wired up to analog port 1, then we have the N-scope wired up to analog port 0 and channel 1 on the N-scope. And then if we go through, I am currently generating a triangle wave. And if we take a look at the processing window, hit 0. So we get another triangle wave. And as we can see, it's aliasing at around, it's generating a harmonic rather, at around 10. And that would mean that each one of these points is due to it being sampled at a peak. So because the sampling rate is 500 hertz, or approximately 500 hertz, and the frequency of the signal itself is 10 hertz, then we are hitting only one sample per area of the peak, and so when we linearly interpolate, we get this. That is the phenomena of a triangle wave. It's stopping just below 5 because the sample rate, as you can see, is about 480 something, and I was up into the 600s with my sample rate on Arduino, so I figured that would be not great to do anymore. Then if we go ahead and change this, because P1 is on, if we change to P1, and that gives us a square wave. And if we go back over to our processing window, get a square wave at pretty much full voltage, and as we can see, the harmonics are infinitesimally, or almost infinitely getting smaller and asymptotically approaching 0. So we're getting more and more higher frequencies, and if you can really look close, you can see the little wiggle there, and that is the, as I demonstrate here. So there's the peaks that it's sampling from the triangle wave, and here is how it makes up for a square wave in sinusoid form.